Okay, so we're going to talk about upstream versus downstream, okay? Kind of explain to y'all what that means. So I drew a river or a stream. We got a beaver dam, and our river, the stream is flowing in this direction. So when I say up the stream, that means I'm going against the stream. I'm going against the flow, up the flow, right? So upstream equals before. So upstream equals before. So if I say that it is upstream of the beaver dam, what I mean is it's before the beaver dam. Okay? So downstream is going to be down the stream, and it's going to be after the beaver dam. So same concept. I have my process piping with my process fluid flowing this way, right? And I'm going to have automatic control valve. So if I say if I say upstream, I mean before that control valve. Upstream of that control valve means before that control valve. I'm going against up the flow path, okay? Downstream is going to equal after. So downstream of that control valve is going to be after, because you're going down the stream. So our flow in our piping is going this way, right? So I'm going to use COVID as an example. When you had to isolate because you had COVID, no one was supposed to come over or come to you, and you weren't supposed to go see anybody. So when we isolate a piece of equipment, that piece of equipment, nothing should be flowing from it and nothing should be flowing to it. Same concept. So our block valves or our isolation points are used to stop flow going to and coming from. They're usually gate valves, and there's going to be one upstream and downstream of your isolation point, and there may even be something that is coming inside your isolation point that you may have to walk off as well. So a block valve blocks flow, and an isolation point is usually one of your block valves. So you have your upstream isolation point, that would be this one right here. We would close it to isolate our control valve, and you have your downstream isolation point right here, or block valve, which you would use to stop your anything from coming from, right, or going to. So we have to stop flow going always. And a bleeder valve is a valve that goes to nothing. It goes straight to atmosphere. So an example of that in our hot unit would be this valve right here. So it has a plug in it, but you see how it comes off your piping and goes to nothing? Okay, I'm going to show you another one. Okay, so right here, this would be an example of a bleeder valve. See, it has a plug in it, but it just goes to nothing, right? Now, this is important. The purpose of a bleeder valve is not to bleed out your system, okay? The same sense on the purpose of your throat is not to hold all of your blood in. But if something happens to your throat or your jugular, you're gonna lose blood, right? You're gonna bleed out. So, same concept. If I open this while my unit was running, I will bleed out my entire unit. That is not the purpose of it. It's just that if we were to open it while we're during normal operations, we would end up bleeding out our whole unit. So the purpose of it is to actually, well, we can use it to connect hoses for purging or for draining. And also it's for verification that our piping is empty or our piece of equipment is empty inside of our isolation points, so that way we know it's safe for maintenance to go and unbolt something or go inside of something, a piece of equipment for maintenance. I'm going to talk a little bit about purging. So I got our shell and tube heat exchanger running. I'm going to go ahead and shut it down and let it drain itself out. Okay, so if you you'll notice we still have green in here, right? So everything else has gravity drained out, but these tubes right here, they're perfectly horizontal. They're not gonna drain by gravity, right? So what we could do is we could use nitrogen or steam to fill up the top of the tubes, fill all this up, and then it will push it out to the low point, okay? So because this is just an illustrator for a shell and tube exchanger, it doesn't have bleeders on it, but what we would do is use fittings. See the fitting on there? We would use fittings to connect to the end of a bleeder valve, connect the hose, and connect the other end to our utility station. Use nitrogen and connect it to a high point bleed. So the high point bleed is something high up, right? The highest point of the process or the equipment. And purge it. We're gonna pressure it up and push the liquid out. Good on that? So a bypass is something that's gonna go around a piece of equipment. If we wanted to bypass traffic, let's say we're traveling down I-10 and the traffic gets really bad, we could bypass traffic by going around, hitting Highway 90, going down 90, and then getting back on after the traffic dies down, right? So we would be bypassing traffic. Same concept, we would be bypassing this control valve, for instance. So our flow is going this way, right? I'm gonna highlight it green or mark it green. So this valve, this line right here, it comes off of our inlet, right? The inlet of our control valve, goes around and ties back into the outlet. So a bypass comes off the inlet, goes around a piece of equipment and ties back in or connects back to the outlet. What about a distribution header, commonly referred to as a header? We're going to use city water as an example. So this is a city water tower, right? And it's going to distribute water all throughout wherever this town is, okay? So it's going to usually be piping that goes underground, right? Let's assume it's over here by Sewella, okay? So you're going to have your pipe going to all the different streets by Broad Street, right? The local police station, all of that, right? And then the gas stations, all the stores, all the houses, right? And then let's go to Sewella's P-Tech department, okay? So we have a women's and a men's bathroom, right? So the women's bathroom has 3 sinks and 3 toilets. So we'll go with that. We got the bathroom, and it's gonna have 3 sinks and 3 toilets, okay? The men's bathroom, we're just gonna go with 1-on-1 because I have no clue what they got in there. We got a toilet and bathroom. Then we have our kitchen, right? We have a sink, and then we have a couple of different outside water hoses, right? So this right here would be our main city water supply header, right? All of this technically is considered the city water header, okay? Our distribution header, right? This right here would be the P-Tech building's city water header, right? Supply header. And it's gonna go to, this is the girls' bathroom, right? This is the men's bathroom. This is our kitchen. And this is all of our outside water hoses, right? A header supplies one thing to multiple users, okay? So the houses, all the sinks, the bathrooms, right? The sinks and the toilets and the different units, right? And the men's bathroom, all of those are users. So let's assume this is actually supplying instrument air to all of our users in the industry. So we'd have our instrument air system, right? So the instrument air system's gonna compress it, remove any moisture, and clean it, right? And it's gonna go to all of the automatic control valves throughout the unit. So again, it's a supply header or a distribution header. It's gonna distribute or supply instrument air to all of the users, all of the automatic control valves or pneumatic control valves in our units. So I'm gonna give y'all some examples of some interlocks. You have permissives, which means this must be met in order for that to happen. So an example, layman's example would be your vehicle. Before you're able to start your vehicle, you have to put your foot on the brake, right? Before you can turn your ignition, you have to put your foot on the brake. Or before you put it in gear, you have to have your foot on the brake. Those are permissives. Let's see, so a co-requisite, that would be like, an example of that would be like a space heater. So, you know, the little portable space heaters that you plug in like your bathroom when it's wintertime. The newer ones have a co-requisite interlock on it, where it has to be up level for it to be on. If it gets knocked over or is on a tilt, it won't allow it to stay on, or it'll trip it and turn it off. A upper limit switch interlock, so a blow dryer, when you're blow drying your hair, or your mama is, or whoever, and all of a sudden the blow dryer kicks off. They're sitting here hitting that reset button, but it's not doing anything. So the reason it kicked off is because it exceeded its high limit temperature switch. It got too hot. So that's an interlock, right? And you can sit there and hit reset all you want. It's not going to turn back on until it gets below that high limit temperature switch. So the temperature has to deviate below that high limit, that upper limit, and then it'll allow it to kick back on. So that's a good example also of a trip, because a trip does not necessarily 90% of the time in the field, it's not going to mean like the breaker tripped, I have to go flip the breaker. No, what's happening is it exceeded some upper or lower limits, and it shut everything down, the interlock did, to protect the equipment or the personnel or the environment.